dear students, welcome to the lecture series on geography. In previous episodes, we discussed regarding the contents in the atmosphere. In this episode, we will concentrate towards the ocean water and their characteristics. There are many similarities between the atmosphere and the oceans. Both are composed of fluids, air or water, which are free to flow under the influence of temperature differentials. Like the atmosphere has winds, so the ocean has currents. Just as the atmosphere has surface winds and upper atmosphere circulation, the oceans also have surface currents and deep water currents. In this lecture, we will examine the ocean water circulation and the reasons behind them under the following subheadings. They are density of ocean water, causes of ocean currents, Coriolis force and ocean gates, deep water currents and ocean currents and climates. Let us start with the density of ocean water. Water is most dense at 4 degrees centigrade. It expands when cooled below this temperature and when heated above this temperature. The oceans are heated from above. These two facts have important implications for ocean circulation. Because water becomes less dense when heated above 4 degrees centigrade, heating from the surface will form a warm, buoyant and stable layer at the surface. There is no tendency towards deep convection and mixing. Conversely, if water is cooled below 4 degrees centigrade, it becomes less dense, so a cold, buoyant and stable layers forms on surface. Water also undergoes a dramatic expansion on freezing, increasing in volume by 9%, so pack ice also forms a stable upper layer. Thus, in many circumstances, vertical motions of the oceans are suppressed. On the other hand, ocean water density is also influenced by salinity. The sea contains dissolved ions, mainly sodium and chlorine, and is consequently denser than fresh water. The salinity of seawater is rather variable. Evaporation at the sea surface will increase the salinity, whereas inputs from rain or river runoff will decrease the salinity. Salinity will also be increased by the formation of sea ice. As ice forms, salt is rejected from the freezing water, so the remaining liquid water is enriched in salt. The density of seawater is thus a combination of its temperature and salinity. Saline waters at around 4 degrees centigrade will be dense and will tend to sink, whereas warm, less saline water will be less dense and thus will be buoyant. This has important implications for vertical motions in the sea. Deep convection, whereby surface waters are transported to the deep oceans, is only possible where saline waters are cooled. To best understand ocean water dynamics or how water moves, there are a few simple principles to keep in mind. Water always flows down towards the lowest point. Water's density is determined by the water's temperature and salinity. Cold ocean water is denser than warm water. Water with high salinity is denser than water with low salinity. Ocean water always moves towards an equilibrium or balance. For example, if surface water cools and becomes denser, it will sink. The warmer water below will rise to balance out the missing surface water. Ocean layers. The ocean can be divided into several layers. The top layer of the ocean collects the warmth and energy of sunlight, while the bottom layers collect the rich, nutrient-filled sediment of decayed plant and animal matter. The top ocean layer is about 100 meters deep. Enough sunlight reaches that depth for organisms such as phytoplankton to carry out photosynthesis. Phytoplankton makes up the first part of the marine food chain and is essential to all ocean life. The middle or barrier layer is called the thermocline. The ocean's temperature and density change very quickly at this layer. The barrier layer is about 500 to 1000 meters deep. Below the barrier layer is the bottom layer, referred to as the deep ocean. It averages about 3 kilometers in depth. Now coming to causes of ocean currents. The ocean is in constant motion. You can see this for yourself when you watch waves crash onto shore. Typically, ocean currents are divided into two types: surface currents, which usually extends no more than about 400 meters below the surface, and deep water currents, also known as the thermohaline circulation, which occur in much deeper layers of the ocean. There are several causes for ocean currents, including solar activity, gravity, and winds. Let us study these causes one by one. Solar activity. This is the single most important cause. The sun provides the bulk of the energy which drives the circulation of water in the oceans, either directly or indirectly through winds. The uneven distribution of solar energy across the globe produces an uneven heating of water in the ocean. Like air, hot water expands. The differential heating is so pronounced that sea level at the equator is about 8 cm higher than at temperate latitudes. Next is gravity. The equatorial bulge of the oceans caused by the expansion of water under equatorial heat creates a slope, and water tends to run downhill under the force of gravity. This is one of the major reasons for surface water flow from the equator towards higher latitudes. Winds. Winds produce a flow of water at the ocean surface due to frictional coupling between the wind and the surface of the oceans. Since the oceans are largely flat expanses clearly by topography, winds can blow for long fetches or distances for prolonged periods of time. The duration of the wind is very significant. Since water is much heavier than air, it also has much more inertia. Short duration winds only produce turbulence at the water surface. It takes winds blowing over a longer duration to produce a sustained movement of water in the wind's direction. So, wind-driven ocean currents are a very significant factor in ocean circulation. Friction between the air and the surface of the water is sufficiently high that a wind blowing for about 10 hours can produce a surface current in the water at about 2% of the wind velocity. So, a steady wind blowing in a certain direction at 20 miles per hour for about 10 hours will produce a surface water current at about 0.4 miles per hour. The direction of the water current is not the same as that of the wind flow. The direction of the water current is affected by a phenomenon known as Ekman Transport. So, what is Ekman Transport? This phenomenon is named after the Swedish physicist V. Wolfrid Ekman, who first described it mathematically in 1905. Ekman based his model on observations made by Norwegian explorer F. Nansen. Nansen discussed his observation with Ekman, who formulated the equations to describe the motions. The deflection of wind-driven currents is now known as Ekman motion. Because the surface layer of the ocean transfers some of its momentum to deeper water, because the surface layer of the ocean transfers some of its momentum to deeper water, and because these deeper layers are subject to Coriolis deflection too, successively deeper layers of the ocean are deflected to the right of the upper layers. The wind-driven currents thus form a spiral called the Ekman spiral, which gradually dies out at depth. The average motion of the Ekman layer is 90 degrees to the right of the wind direction in the northern hemisphere. The Ekman spiral indicates that each moving layer is deflected to the right of the overlaying layer's movement. Hence, the direction of water movement changes with increasing depth. In an ideal case, a steady wind blowing across an ocean of unlimited depth and extent causes surface waters to move at an angle of 45 degrees to the right of the wind in the northern hemisphere. Ekman Transport piles up surface water in some areas of the ocean and removes water from other areas, producing variation in the height of the sea surface, causing it to slope gradually. One consequence of a sloping ocean surface is the generation of horizontal differences in the water pressure. These pressure gradients in turn give rise to geostrophic flow. Next, we shall move on to Coriolis force and ocean gates. This is a pseudo force resulting from the Earth's rotation from west to east about its axis. Because of the Earth's rotation, any movement away from the equator is deflected eastwards, while movement towards the equator are deflected westwards. This effect is very pronounced in the movements that happen within the fluid medium and over long distances. Because of the Coriolis effect, currents tend to flow in curves rather than in straight lines. When the space for movement is restricted, these curves can close on themselves and cause a circular flow of water around a center. Such circular flows are called oceanic gates. There are many permanent gates in the world's oceans. Their locations are dictated by the temperature of the water and the ocean land boundary. Gates are usually bounded by the shallow waters and continental shelves. There are 5 major gates in the world's ocean which are delimited by the continents around them. These gates are responsible for much of the world's surface currents. The wind blows across the ocean and moves its water as a result of its frictional drag on the surface. Ripples or waves cause the surface roughness necessary for the wind to couple with surface waters. A wind blowing steadily over deep water for 12 hours at an average speed of about 100 cm per second would produce a 2 cm per second current. If Earth did not rotate, frictional coupling between moving air and the ocean surface would push a thin layer of water in the same direction as the wind. This surface layer in turn would drag the layer beneath it, putting it into motion. This interaction would propagate downward through successive ocean layers like cards in a deck, each moving forward at a slower speed than the layer above. However, because Earth rotates, the shallow layer of surface water set in motion by the wind is deflected to the right of the wind direction in the northern hemisphere and to the left of the wind direction in the southern hemisphere. This deflection is known as Coriolis effect. Except at the equator, where the Coriolis effect is 0, each layer of water put into motion by the layer above shifts direction because of the Earth's rotation. The 5 ocean gates are the source of most of the ocean currents in the world. However, there are smaller currents that are produced as the result of local heating or cooling or because of the presence of landforms which cause the main currents to split into two. Coming to deep water currents. The currents we have talked about so far are surface currents driven mostly by temperature, winds and gravity, and modified by things such as Coriolis effect and by continental shorelines. On the other hand, in addition to these surface currents, there is also a deep water circulation in the oceans referred to as the Thermohaline Circulation or sometimes the Oceanic Conveyor Belt. As the word thermohaline indicates, where thermo means heat, haline means salts, this circulation is driven mostly by temperature and salinity of the water. The deep underwater currents are more massive but more slowly than surface currents. Underwater currents mix the ocean water on a global scale. A process known as thermohaline circulation or the ocean conveyor belt drives these deep underwater currents. Thermohaline circulation moves a massive current of water around the globe from northern ocean to southern oceans and back again. Currents slowly turn over water in the entire ocean from top to bottom. It is somewhat like a gain conveyor belt moving warm surface waters downward and forcing cold, nutrient-rich water upward. The term thermohaline combines the words thermo and haline, both factors that influence the density of seawater. The ocean is constantly shifting and moving in reaction to changes in water density. The oceans are in constant motion both from winds that generate waves and currents and forms and pull of gravity that creates the tides. A factor, thermohaline circulation, occurs deep within the ocean and acts like a conveyor belt as ocean absorb, store and redistribute vast amounts of sun's heat around the globe. Without this, places at the same latitude across the globe would generally have the same average temperatures. Thermohaline circulation is driven by changes in the density of seawater. The conveyor belt transfers warm water from the Pacific Ocean to the Atlantic as a shallow current and returns cold water from the Atlantic to the Pacific as a deep currents that flow further south. Beginning in the central Pacific, it travels past the north coast of Australia and around the southern tip of Africa before moving up into the Atlantic. By the time it heads up the Atlantic, it turns into the Gulf Stream. As it passes Europe, the surface water evaporates and the ocean water cools, releasing heat to the atmosphere. This release of heat is largely responsible for the relatively warm temperatures enjoyed by Western Europe. As the water becomes colder, it increases in salinity and becomes dense, sinking thousands of meters below the surface. The deep water slowly travels south through the ocean deep hole, eventually mixing upward to the surface in different parts of the world up to 1,000 years later. The ocean conveyor belt plays a crucial role in helping to shape the Earth's climate. However, global climate changes could alter or even halt the current as we know it today. As the Earth heats up, there could be an increase in precipitation and a melting of freshwater ice in the Arctic Ocean, which would flow into the Atlantic Ocean. This additional fresh water could dilute the Atlantic Gulf Stream to the point where it would not continue to sink into the depths of the ocean. It takes about 500 years for the conveyor belt to turn over the ocean waters and make one complete trip around the earth. One effect of thermoclines or haloclines is to prevent the mixing of water from different layers. This can have important effect on oxygen levels. Deeper waters have low oxygen levels because organisms living those waters use up the oxygen, and the thermocline or halocline prevents surface water which is rich in oxygen from passing into the layers below. Now we can concentrate on ocean currents and climate. The transport of water in ocean currents also transports heat. Warm currents flowing poleward transport heat to colder region, whereas cold currents flowing equatorwards have the opposite effect. Another way in which oceans can influence weather systems is in the formation of tropical cyclones. These immensely destructive rotating storms forms only where the sea surface temperature is about 27.5 degrees centigrade, because it is only here that enough energy can be supplied to fuel the intense convection required to trigger these storms. El Nino has gained a reputation as a huge climate disruption, causing severe disruption of accustomed weather pattern. El Nino originally referred to a warm west to east surface current that appeared off the coast of Peru around Christmas. El Nino conditions recur about once in every 5 to 10 years, although they have become more frequent and long-lasting since the 1970s. El Nino is an example of an atmospheric oceanic oscillation which brings about cyclic changes in weather patterns and ocean circulation. There are other large-scale oscillations such as Arctic oscillation, which affects wind and weather pattern in the North Atlantic and Pacific Oceans, and many underlying patterns of flooding in Europe. Ocean temperature plays a key role in the conveyor belt, so a change in the Earth's climate might have drastic effect on the system. If one part of the conveyor belt breaks down, if cold water is not lifted to the surface in upwelling, nutrients will not be distributed to start the food chain. Organisms such as phytoplankton need those nutrients to thrive. Severe climate change slows phytoplankton from forming the first link in the marine food chain. If the first link is threatened, all life in the oceans is threatened. Our climate is very much dependent on ocean current, since they redistribute massive amounts of heat energy from one part of the earth to another. A disruption of ocean currents would lead to dramatic changes in the climate. Ocean currents have a serious impact on our life. They are responsible for the accumulation of nutrients in rich patches which are prime fishing grounds. These ocean currents affect marine life as well. The migration of many organisms in the sea follows various currents in the oceans. Traveling along the path of a current is energy efficient and fast. They also affect the fishing industry. Obviously, fishing along the migration path of a commercial species can be a good idea if implemented at the right time. Also, currents have an effect on nutrient levels in the ocean, which can affect the density and diversity of sea life. In areas where these surface currents move away from the coast, there is an upwelling of deep sea water. Deep sea waters are rich in nutrients, and so these places are very rich in marine life. Some of the world's best fishing areas are located in places where a current moves away from the shore. Finally, coming to conclusion. Water plays a central role in the climate system. Its density varies depending on salinity and temperature. Cold, salty water is heavy and sinks to greater depth. This causes the circulation of millions of cubic meters of water in the ocean. Ocean currents transport enormous amounts of heat around the world. This makes them one of the most important driving force of climate. Because they respond extremely slow to changes, the effect of global warming will gradually become noticeable, but over a period of centuries. Climate changes associated with wind and sea ice could become recognizable more quickly. So students, hope you got some information about ocean water circulation. Thank you for watching this session. Hope we will meet in future episode. Until then, take care. Thank you.